This lecture is the continuation of our last lecture. In the last lecture, we have talked about random variable with discrete case. In this lecture, we will discuss the situation wherein both random variables are continuous in nature. Therefore, these have continuous distribution. Any number can be considered as a random variable if it is performing some random experiment. We already considered different concepts of probability in connection with a single random variable. For two random variable, we have extended this concept to bivariate random variable. The outline of today's lecture is first we will talk about two random variables, then the joint cumulative distribution function of two random variable in continuous case, then independent random variable, the cumulative distribution of two independent random variable, then the joint cumulative distribution function properties we will discuss, then the marginal distribution function, then its properties, then joint probability density function, the properties of joint probability density function. Thereafter we will discuss the marginal probability density function, and finally we will discuss the conditional probability density function and the example related to the continuous random variable. First, two random variable in a continuous situation, when we are dealing with the continuous world, suppose S is a sample space, we can map it into the two-dimensional xy plane. So the x and y are the pair of a joint random variable. The examples for the continuous random variables are time taken something to be done, the distance traveled in given time. Such an example can be described by the two random variable in continuous situation. Now let us talk about the joint cumulative distributive function of a continuous random variable. The joint cumulative distribution function or the joint CDF of two random variables, suppose x and y, is denoted by f sub of x and f sub of x of xy in the function defined by. So its definition is the probability of x is less than or equal to small x and y is less than or equal to some number that is small y. This is equal to the cumulative distribution function or the cumulative CDF of two random variable x and y. The event when x is less than or equal to some value x and y is less than or equal to some small y is equivalent to the A intersection B, where A and B are some events of sample space S. Then the event A is equal to, there is some zeta belongs to the sample space S. The x of zeta is less than or equal to small x, and similarly the event B is also from sample space S, and there is some number that is a zeta that belongs to the sample space S, such that y of zeta is less than or equal to y. Then the probability of this random variable A is equal to the cumulative distribution function CDF of x. Similarly, and the probability of event B is equal to the CDF of y. So the cumulative CDF are the joint CDF of two random variable x and y is represented f sub of xy of x and y is equal to the probability of the A intersection, two events A and B intersection, the probability of the intersection of two events A and B. For particular value of x and y, the A and B are independent event of sample space S, then the product of the CDF of X and CDF of Y should be equal to the joint CDF of X and Y. So these properties should fulfill the joint distribution function, joint cumulative distribution function. So if these properties are fulfilled, then we can say the function is a joint cumulative distributive function. Next, independent random variable, as we have already talked, two random variable X and Y are called independent if the product of the cumulative distribution of X, CDF of X, the product of CDF of X and Y is equal to the joint CDF of X and Y for every value of X and Y. Now the properties of the joint cumulative distributive function can be defined. The joint CDF of two random variable have the following properties. First, the joint CDF is greater than or equal to 1 and it is less than or equal to 1. So it lies between 0 and 1. So the minimum value is 0, its maximum value is 1. So if two numbers x1 is less than or equal to x2 and y1 is less than or equal to y2, then the CDF of x1 and y1 is less than or equal to the CDF of x2 and y1, which is less than or equal to the CDF of x2 and y2. So the highest CDF is for the values of x2 and y2. Similarly, CDF of x1 and y1 is less than or equal to the CDF of x1 and y2, which is less than the CDF of x2, y2. Another property is that when x approaches to infinity and y approaches to infinity, then the CDF of x and y random variable is equal to 1. Similarly, also as x approaches to minus infinity, then the CDF of x and y is equal to 0 if the limit of one of the random variable is infinity, then the joint CDF of the two random variable would be 0. So next, when one of the random variable approaches to some number a, here we use a plus, then the CDF of joint CDF of two random variable can be described as f sub xy of a and y. So if the CDF, if x1, if some random variable x is greater than x1 and it is less than or equal to x2, and random variable y is less than y less than or equal to y, then their joint probability or the joint CDF is defined as this is the probability of x and y, which is equal to the CDF, joint CDF of x and y of x2 and y minus f sub xy, x1 and y, x1 and y. Similarly, if x is less than or equal, the probability of x is less than or equal to small x, y1 is y is greater than y1 and it is less than or equal to y2, then their joint CDF is equal to f sub xy, x comma y2 minus f sub xy, x comma y1. If x1 is less than are equal to x2 and y1 is less than or equal to y2, then their the joint CDF can be described as f sub xy x2 y2 minus f sub xy x1 y2 minus f sub xy x2 comma y x2 y1 plus f sub xy x1 y1 which is greater than or equal to 0. So the CDF must have fulfill these properties. If some function or some CDF fulfill these properties, then we can say that it is the joint CDF function. Now let us talk about marginal distribution function. If the limit y approaches to 0, if we are talking about the joint CDF of x and y, if the y approaches to infinity, then the joint CDF is equal to the CDF of random variable x. And similarly, if the limit x approaches to 0, then the joint CDF must be equal to if the random variable x approaches to infinity, then the joint CDF would be equal to the CDF of y. Fx and f sub x of x and f sub y of y are referred as the marginal CDF of random variable x and y. Now let us talk about the joint probability density function. It is also called the joint PDF. Let x and y be a continuous bivariate random variables with CDF, with their joint CDF f sub of xy of xy, and if we take the then it's the PDF of this joint CDF would be equal to by taking the second derivative, by taking two derivatives, one derivative with respect to random variable x and the other derivative with respect to random variable y, then this CDF change to the PDF of joint PDF of density function. The function, this function is called the joint probability function or the joint PDF, probability density function or the joint PDF of x, y. So by integrating the PDF with respect to x and with respect to y, then we get the CDF of joint CDF of random variable x and y. The following are the properties of the joint PDF. First, the joint PDF of two random variable x and y must be greater than or equal to 0. Also, by integrating the joint this joint PDF from minus infinity to infinity along x direction, and similarly the variable y integrating from minus infinity to infinity. So it gave us the result is equal to 1. The probability is 1. Also, the joint PDF is a continuous for all value of x and y except possibility a finite set. So the probability of two random variable x and y, if x and y belongs to some event a, then it can be described the range of a by integrating the range of a along x and y. So it gave the probability of that event a. So if the probability of random variable x is greater than a and less than or equal to b, and random variable y is greater than c and less than or equal to d, then its CDF or the probability, the joint CDF can be attained by integrating the PDF from a to b and c to d along x and y direction. Also, if the probability of x is greater than a and less than b, and random variable y is greater than c and less than or equal to d, so its probability, we can write it as integrating the random variable along x and y, x is from a to b and c to d. Next, the marginal probability density function. The marginal PDF is defined as, if we know that the CDF, marginal CDF, when one of the if the random variable y approaches to infinity, then the joint CDF change into the CDF of the random variable x, and it can be further also it can be attained by integrating the joint PDF of two random variable. Suppose integrating the random variable y from minus infinity to infinity and the random variable from minus x to x, so this is equal to the joint this is equal to the marginal PDF of x. By taking the derivative of the marginal CDF of x with respect to x, it gives the marginal PDF of random variable x. So similarly, we can get the PDF of the random variable y, or integrating the joint PDF of random variable x and y with respect to integrating from minus infinity to infinity with respect to y, it gives the marginal PDF of x. Similarly, integrating from minus infinity to infinity along x direction, it gives the marginal PDF of random variable y. So independent random variable, if x and y are independent random variable, then their joint CDF is equal to the product of marginal CDF of x and marginal CDF of y, or also their PDF, joint PDF is equal to the product of marginal PDF of random variable x and y. Now let us talk about the conditional probability density function. If random variable x and y are continuous bivariate random variable with joint PDF as f sub xy of xy, then the conditional PDF of y given x, if x is equal to some number small x, then the conditional PDF f sub y given x is equal to the joint PDF of x and joint PDF of x and y divided by the conditional PDF of the PDF of random variable x. Similarly, as such, f sub x is greater than 0. Similarly, the conditional PDF of x given y is equal to the joint PDF of x and y divided by the PDF of y, whereas PDF of y is greater than 0. Their properties is the conditional PDF is greater than or equal to 0. By integrating it from minus infinity to infinity, the conditional PDF is equal to 1. Let us talk about an example. Consider a function, the CDF, which is equal to 1 minus e raised power x e raised power minus x minus y, which when x is greater than 0 or equal to 0 and less than infinity. Similarly, y is greater than or equal to 0, less than infinity. Otherwise, this function is 0. Can this function be a joint CDF of bivariate random variable x and y? To ensure whether this function is a joint CDF or not, we have to check whether this function fulfills the properties which we have already defined. The first property is that this the joint CDF is greater than or equal to 0 and less than or equal to 1. So when I incorporate here x is when x and y are infinity, or x or y is infinity, this function is equal to 1, and when x and y are equal to 0, so this function would be equal to 0. So this satisfy the property number 1. The property number 2 is x1 is less than or equal to x2 and y1 is less than or equal. Then this f sub xy, x1, y1 is less than or equal to f sub xy, x2, y1. So when I incorporate here the x1 and x2, so it fulfill this property. Similarly, when x approaches to infinity and y approaches to infinity, this function should be equal to 1. So also this satisfies this property. And also another property, when x approaches to minus infinity, then this function should be equal to 0. So when I incorporate here x approaches to minus infinity and y approaches to minus infinity, so I will get this function 1 minus 1 should be equal to 0. So another property which we have, the last property, which is when x1 is less than x2, y1 is less than y2, then the joint CDF, I will get this joint CDF. This should be greater than or equal to 0. So when I apply this property, it is obvious that this function is less than 0. Hence, I can say that the function is not a joint CDF of a bivariate random variable. Let's talk about another example. In this example, the joint CDF of bivariate random variable x and y is given as when x and y are greater than or equal to 0 and alpha and beta are greater than 0. Find the marginal CDF of x and y. By taking the marginal CDF of x, the y should be infinity when I will incorporate infinity. So this term will vanish. This would be equal to 0. So the marginal CDF of x is equal to 1 minus e raised power minus alpha when x is greater than 0. Otherwise, it is 0. So when variable x is equal to infinity, then the marginal CDF of y is equal to 1 minus e raised to power minus. This term will vanish. So when I will multiply 1 with this term, I will get 1 minus e raised to power minus beta. Next, in the B part, show that x and y are independent variables. So we know from the property the product of the marginal CDF of x and y should be equal to the joint CDF of x and y. So when I multiply f of x and f of y, so I will get the same. The product is same as the joint CDF of x and y. So I can say that x and y are independent random variable. Next, in C part, I have to find the probability of x. Probability of x is less than or equal to 1, y is less than or equal to 1. So I will incorporate x is equal to 1 here and y is equal to 1 here. So I will get CDF f sub x y 1 of 1 and 1 is equal to this. So when x is less than or equal to 1, so the CDF would be equal to 1 minus e raised to power minus alpha. I will incorporate x is equal to 1 here, and y would be equal to infinity, so I will get this. When so similarly for probability of y greater than 1, so that is equal to 1 minus probability of y less than or equal to 1, which is equal to 1 minus CDF of y of 1, CDF of y when y is equal to 1. So this is equal to e raised to power minus beta. By incorporating here, I will get CDF is equal to e raised to power minus beta. It's quite simple. Next, the last part is when probability of x is greater than x and y is greater than 1. So the event when x is greater than x and intersection of y is greater than y, its complement is equal to x is greater than x complement with union y is greater than y with its complement. So this is equal to this thing is equal to x is less than or equal to x with union y is less than or equal to y. So this event can be described like this. So when I will take the probability of this event, so I will get the probability of x is less than or equal to x plus probability of y is less than or equal to y minus probability of x is less than or equal to y, the joint probability of x and y. So by solving this, I will get 1 minus e raised to power minus alpha into x into e raised to power minus beta into y. So when I will incorporate in this formula, so the probability of x is greater than x and y is greater than y is equal to 1 minus probability of x is greater than x with intersection y is greater than y whole complement. So this would be equal to e raised to power minus alpha into e raised to power minus beta. Now let us talk about another example. We have to find the joint CDF of bivariate random variable x and y given. The CDF is equal to the joint CDF of x and y is equal to 0 when x and y are less than 0. It is equal to P1 when x is greater than or equal to 0 and less than some number a, and y is greater than or equal to 0 and less than b. It is equal to P2 when x is greater than a and y is greater than or equal to 0 and less than b. This CDF is equal to P3 when x is greater than 0, greater than or equal to 0, less than a, and y is greater than b. And this CDF is equal to 1 when x is greater than a and y is greater than b. Find the marginal CDF of x and y. So first let's talk about the marginal CDF of x. For marginal CDF of x, the y should be equal to infinite. So in this case, when x is less than or equal to when x is less than or equal to 0 and less than a and y is greater than b, here we can incorporate infinity. So we will get the conditional marginal CDF of x is equal to P3 when x is less than or equal to greater than 0 and less than a, and when it is less than 0 it should be 0. When x is greater than a1 it should be equal to 1. So similarly, the marginal CDF of y we can get by incorporating x is infinite. Here when x is greater than a it should be infinity. So I will get incorporating x is equal to infinity in this equation. I will get when x is greater than a, when I will put infinity here, so I will get the marginal CDF of y, and here I mean when x is greater than a, we will put this as infinity. A is infinity, I mean equal to infinity. When x is equal to infinity, then the conditional CDF of y, I can write it is equal to 0 when y is less than 0, and it is equal to P2 when y is greater than 0, greater than or equal to 0 and less than b, and it is equal to 1 when y is greater than or equal to b. So in the b part, find the condition on P1 and P1, P2 and P3 for which x and y are independent. So for x and y to be independent, we must have the product of the marginal probability of x and the marginal probability y, their product should be equal to the joint CDF of x and y. So the marginal CDF of x is equal to this and marginal CDF of y is equal to this. So when we will take the product, so the product of P2 and P3 should be equal to 1, then we can say that the random variable x and y are independent. Now let us talk about another example. The joint PDF. Now let us talk about the PDF, probability density function of a bivariate random variable x and y, which is equal to a into x plus y when x is greater than 0, less than 2, and y is greater than 0 and less than 2, otherwise it is equal to 0. Where k is a constant, find the value of k. First we have to find the value of k, find the marginal PDF of x and y, or x and y are independent. So in the first case, to find the value of k, we know that integrating this PDF from minus infinity to infinity along x and y direction, we will get this would be equal to 1. So as we integrate it from minus infinity to infinity, so the limits are from 0 to 2. So when we will integrate it, I will integrate this PDF, so eventually I will get 8k is equal to 1. So the value of k must be equal to 1 over 8. Now next I have to find the marginal PDF of x and y. So the marginal for the marginal PDF, I will integrate it from for the marginal PDF of x, I will integrate it from minus infinity to infinity along x direction, or along for random variable y. So when I will integrate it, I will get I will integrate it from 0 to 2. I will get the marginal PDF of x, that is equal to 1 over 4 into x plus 1 when x lies between 0 and 2, otherwise it is equal to 0. Similarly, I can find the marginal PDF of y, which is equal to 1 over 4 y into y plus 1. So next part is we have to find are x and y are independent. So in this case, the product of the marginal PDF of x and y should be equal to the joint PDF of x and y. So when I will take the product of marginal PDF of x and y, it must be equal to 1 over 8 into x plus y. So this is not equal to the joint PDF of the product of marginal PDF of x and y is not equal to the joint PDF of x and y, which is obvious. 1 over 4 multiply 1 over 4 is equal to 1 over 16 when I multiply x plus 1 into y plus 1. So this is not equal to the joint PDF of x and y. So I can say that x and y are not independent. So the joint Another example, the joint PDF of bivariate random variable x and y is given that f sub x y is equal to k of x and y when x and y are greater than 0 and less than y, otherwise it is equal to 0. So I have to find the value of k. What I will do, I will integrate it from minus infinity to along the minus infinity to infinity along the x direction, and in the y direction I will for y random variable I will integrate it from minus infinity to infinity. Then it should be equal to 1. So the limits are given from 0 to 1. So I will integrate it from 0 to 1 along x variable, and I will integrate it from 0 to 1 along y variable, and it should be equal to 1. So in this way I can find the value of k. Then I have to find the value, or x and y are independent, then the product of the marginal PDF of x and y should be equal to the joint PDF of x and y. In the C part I have to find the probability when x plus y is less than probability of x and probability when x plus y is less than 1. So in the first case, when I will integrate it integrate the PDF, I will get k by 4 is equal to 1. So the value of k is equal to 4 in this case. In order to determine the marginal PDF of x, I will integrate this joint PDF from 0 to 1 along y variable, so along y direction. So I will get 4xy, so I will get the marginal PDF of x is equal to 2x. Similarly, the marginal PDF of y is equal to 2y. So if I take their product of the marginal PDF of x and y, it should be equal to the joint PDF of x and y. So which is obvious, 2 multiplied 2 is equal to 4, 2x multiplied 2y is equal to 4y, so which is equal to the joint PDF of x and y. So I can say that x and y are independent. Now the C part was I have to find the probability x plus y random variable is less than 1 for this case. So in this case, when x is, this is along y axis, this is along x axis, so this is equal to when x is equal to y is equal to 0 and x is approaches to 1, and in this case here y is equal to 1 and y is less than, here y should be less than, is near to 1, approaches to 1, and x is equal to 0. So I will integrate it from 0 to 1 along y direction, and we will integrate the PDF the PDF from 0 to 1 along the x direction. So I will get the probability of x plus y random variable less than 1, which is equal to after solving I will get this one is equal to 1/6. That's it. We will further explore the two random variable in the next lecture, and that's it.